Welcome to this explainer. Today, we are stepping into the ring for the ultimate physics boxing match. Your opponent? The Cambridge Physics exam. Whether you are tackling syllabus 0625, 0651, 0652, 5054, or even looking ahead to 9702, the strategy is exactly the same. You have to float like a concept and sting like evidence. You need combinations: jab, cross, hook. You can't just throw wild punches and expect to get the marks. To prove this, we are going to dive deep into one of the most notoriously tricky topics out there, the invisible world of waves, straight from the Master Physics Lab notebook. I want you to beat two students who are taking this exam today. First, we have Alex. Alex overloads every single answer with raw physics facts, but gives absolutely zero analysis. It's a data dump. Then we have Sam. Sam rushes, panics, and completely misses the command word requirements. Throughout this explainer, we are going to look at their flawed answers side by side, covered in red pen marks, and I'm going to show you how to transform them into knockout 100% responses. So grab your mental lab coat and your boxing gloves because we are diving right in.
Let's start with a brutal, high-mark question that might just blow your mind, and it's a classic Cambridge past paper scenario. Why is the sun visible for about 2 minutes after it has already sunk below the horizon? It sounds like magic or a glitch in the matrix, right? Now, if we look at our students, Alex wrote a massive paragraph detailing the nuclear fusion of the sun, the exact speed of light, and the distance to the Earth. Total marks? 0. None of that answers the specific question. Sam, on the other hand, just scribbled because the light bends in the sky. Total marks? Maybe 1, if the examiner is feeling incredibly generous. They both missed the incredible power of refraction, and more importantly, they completely failed to structure their answers to grab the marks that are sitting right there on the table. This phenomenon proves physics is happening all around us every single day, but to get the grade, you have to know how to explain it.
Here is our roadmap, or rather our 5 training rounds for today's session. Round 1, water waves and ripple tanks. Round 2, light reflection and refraction. Round 3, focusing light with converging lenses. Round 4, measuring the speed of sound. And round 5, visualizing pitch and loudness. Let's get straight to the lab.
Section 1. Water waves, ripple tanks. Visualizing the invisible. This is where we start building our exam strategy.
To study waves, we need a controlled environment. Enter the ripple tank. We use a transparent tray filled with just about 5 millimeters of water. By shining a light source from above, we can cast the shadows of the water waves onto a white screen below. But waves move fast. That's where the brilliance of this setup comes in, the stroboscope. It's a rotating disc with slits. When you rotate it at a speed so that you view the screen exactly when the waves have advanced 1 wavelength, the moving ripples appear perfectly frozen or stationary. This lets us easily observe and sketch the wavefronts. Now, how do we write about this in an exam? This is where I'm revealing our ultimate strategy, the Peel framework. Point, evidence, explanation, link. When an exam asks you to describe an experimental setup, top students don't just list equipment. They make a point. We use a stroboscope. They provide evidence. It is a rotating disc with slits. They explain, rotating it at the same frequency as the waves freezes the image. And they link it back to the question. This allows accurate measurement of the wavelength. It's a combination punch. And hey, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Let's look at some data you might have to interpret. What happens when we mess with these frozen waves? We observe 2 massive physical concepts. First, if we put a glass plate in the water to create a shallow region of just 1 millimeter, the waves change direction. They travel slower in shallow water, and their wavelength visibly shortens. That's refraction. Next, if we put an obstacle with a narrow gap in the tank, about the same width as the wavelength, the waves don't pass straight through. They spread out significantly. But with a much wider gap, they pass through with far less spreading. That spreading effect is diffraction. Now, interactive time. Look at these facts. If the examiner asks, describe and explain the effect of a narrow gap on a water wave, you have 30 seconds in your head right now to formulate a Peel response. Don't be like Alex and just dump facts about shallow water when the question asked about gaps. And don't be like Sam and just say it spreads. You need to say the wave diffracts. It spreads out in a semicircular pattern. This occurs because the gap is comparable to the wavelength of the water wave. Boom, full marks.
Section 2. Light, reflection, and refraction. Bending beams. This is where we initiate Act 3, the transformation. We are taking those red marks and turning them into green check marks. Before we bend light, we have to bounce it. The golden rule here is the law of reflection, which states that I equals R. If you shine a ray of light at a plane mirror, I is the angle of incidence, the angle between your incoming ray and an imaginary perpendicular line called the normal. The reflected ray bounces off at angle R, the angle of reflection. According to the lab data, these two angles are always exactly equal. Keep in mind, the image you see in that mirror is virtual, meaning it cannot actually be projected onto a physical screen. In an exam, if the command word is state, you do not write a paragraph. You literally just write angle of incidence equals angle of reflection. One quick jab. That's it. Move on and save your time.
Now, what happens when light passes through something? Instead of bouncing off, it refracts, just like our shallow water waves. To measure this, we use the refractive index, denoted by the letter N. This index is simply a measure of the amount of refraction that occurs when light passes between two different media, say from the air into a dense rectangular glass block. When the exam command word is defined, they are looking for absolute precision. You need to hit the exact syllabus definition. You write, it is the ratio of the speed of light in a vacuum to the speed of light in the medium. No fluff, just the knockout fact.
Let's look at the math because the command word calculate is going to show up. The formula is N equals the sine of angle I divided by the sine of angle R. I is the angle of incidence in the air, and R is the angle of refraction inside the medium. By drawing the path of a light ray entering a glass block, marking the normal line, and carefully measuring those angles with a protractor, we calculate the exact refractive index. Now, listen closely. When calculating, Sam always loses marks because Sam forgets to write down the formula first and then forgets the units, or in this case, the fact that refractive index has no units. Always write the formula. Show you're working. It's your safety net. If you punch the wrong number in the calculator, the examiner can still give you method marks. And, speaking of making sure you get every single thing right, stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's trace the complete journey of a light ray through that block and finally solve our sunset question from the beginning. When light enters the denser glass from the air, its speed decreases and the ray is bent towards the normal line. When it leaves the glass block and re-enters the air, its speed increases again and the ray is refracted away from the normal. Because the opposite faces are parallel, the emerging ray travels parallel to the original incident ray. Now let's look at the physics success blueprint and rewrite Alex and Sam's failed sunset answers live. We need green check marks. The question was, why is the sun visible after it has set? Using our PEL framework. Point, the Earth's atmosphere acts like a refractive medium. Evidence, the density of the atmosphere changes, being denser closer to the Earth's surface. Explanation, as light from the sun enters the denser atmosphere, its speed decreases and it refracts, bending towards the normal, curving over the horizon. Link, therefore, the bent light reaches our eyes, creating a virtual image of the sun above the horizon, even after it has physically dipped below it. Look at that. 4 clear, distinct points. 4 guaranteed marks. We just transformed a 0 into 100% by structuring our physics knowledge correctly.
Section 3. Focusing light. Converging lenses. Creating images. It's time for Act 4 of our session, the interactive workshop. I'm gonna put you on the clock. Lenses are the magic behind cameras, telescopes, and your own eyes. To use a lens, you must first find its focal length. This is defined as the distance between the center of the lens and the sharp image formed by nearly parallel light rays coming from a very distant object. In the lab, you hold the lens up to a window, focus the distant landscape onto a piece of card, and measure the distance from the lens to the card. Here is Challenge 1, the data scan. You have 60 seconds in your mind to extract the core trend here. If the light rays from the distant object are parallel, what does that tell us about the image on the card? The trend is that the image forms exactly at the principal focus. The distance measured is exactly the focal length. If an exam gives you a ray diagram with parallel lines hitting a convex lens, you immediately know they converge at F. That is your anchor point for any ray diagram question.
Once we know the focal length F, we place a lit object at different distances. Place beyond twice the focal length, 2F. The image is real and inverted. Move it closer, the magnification changes dynamically. Placed between F and the lens, the image becomes virtual and cannot be formed on a screen. All right, Challenge 2, find the flaw. I'm going to read you Sam's paragraph describing a magnifying glass. Tell me where Sam loses the mark. To use a converging lens as a magnifying glass, you place the object between the focal point and the lens.
The light rays refract through the lens and converge on a screen on the other side to create a large, upright image. Did you catch it? Where is the flaw? The sentence losing marks is converge on a screen. As our slide clearly states, an object between F and the lens creates a virtual image. Virtual images cannot be projected onto a screen. The light rays only appear to diverge from behind the object. The examiner will mercilessly dock a mark for that single incorrect word. Precision is everything.
Section 4. Sound. Measuring the speed. Catching the invisible. Let's move from light waves to longitudinal sound waves and get ready for our final interactive challenge.
Sound travels fast, so in the lab we set a trap. We place 2 microphones exactly 1 meter apart. You tap a hammer sharply on a metal plate near the first microphone. The instant the sound hits that start mic, an electronic timer is triggered. The sound wave rips through the air to the second mic, which instantly stops the timer. Welcome to Challenge 3, Speed Writing. You have a 30-second mental timer counting down right now. I want you to write 1 perfect Peel paragraph explaining why we use 2 microphones instead of a human with a stopwatch to measure the speed of sound over 1 meter. Go. Think about the point. Think about the evidence from the physical world. Explain the mechanism. Link it to accuracy. Time is ticking. Imagine the exam clock. 10 seconds left. All right, time's up. Let's see if your answer matches the perfect formula on the next slide.
Before we evaluate your paragraph, let's look at the math. Velocity equals distance divided by time. The distances are known 1 meter. We take our recorded time, convert milliseconds to seconds, and do the math to find the speed of sound. This brings us to Act 5, the final system. Rule number 1 that guarantees top marks is command word decoding. If a question says calculate the speed, you use this formula and give a number. But if the question says explain why an electronic timer is used, you cannot just do math. You have to decode what the examiner is asking for, which is a justification of the experimental method.
Here is the answer to your speed writing challenge and Rule 2, Peel Framework Application. Did your answer look like this? Point. An automatic timer must be used to eliminate human reaction time. Evidence. Sound travels roughly 340 meters per second, meaning it covers 1 meter in about 3 milliseconds. Explanation. Human reaction time is approximately 200 to 300 milliseconds, which is vastly slower than the event being measured. Link. Therefore, using a timer with millisecond precision ensures the calculated speed is valid and not obscured by human delay. If you wrote something close to that, you just secured 3 or 4 marks. Alex would have written a page on the history of stopwatches. Sam would have written, humans are slow. You used the system, you got the marks.
Section 5. Sound. Pitch and loudness. Seeing sound waves. This brings us to Rule 3 of our final system, the time management matrix. You should be spending roughly 1 minute per mark on your exam paper. By efficiently structuring your Peel answers, you buy yourself time to tackle the tricky, high-mark analysis questions at the end of the paper, like interpreting complex data from a machine.
Speaking of complex machines, enter the cathode ray oscilloscope, or CRO. This incredible instrument takes the electrical signal from a microphone, which is essentially an alternating voltage, and displays it graphically. It shows exactly how the sound waves vary with time. By sounding a pure note from a tuning fork into the microphone, the CRO plots a perfect, continuous wave on its screen. We have successfully made the invisible visible. In an exam context, questions about the CRO are designed to test your spatial reasoning. The examiner is going to give you a wave on a grid and ask you to draw what happens when the sound changes. Let's look at how to tackle that.
This brilliantly illustrates the anatomy of a sound wave. If you switch to a tuning fork with a higher pitch, the oscilloscope shows an increase in frequency. You will literally see more waves squished together, fitting across the horizontal axis of the screen. But what if you just hit the tuning fork harder? A louder sound doesn't change the frequency, it changes the amplitude. The waves on the screen get taller, stretching the vertical height of the peaks and troughs. Pitch is frequency, loudness is amplitude. Now listen to me. We have covered our 3 rules: command word decoding, the Peel framework, and the time management matrix. Students who implement these exact physics strategies see an average improvement of 2 whole grade boundaries. But that only happens if they practice consistently with our weekly videos.
To wrap up, I want to leave you with a fascinating high-level thought experiment straight from the physics syllabus. When a police car, sounding its siren, races past you and speeds away, why does the note of the siren appear to drop in pitch? Think about what we just learned about frequency and wavelengths on the CRO. How does the physical motion of the car physically stretch out those sound waves before they hit your ear, lowering the frequency? That is the Doppler effect, and it's a perfect topic to practice your new PL framework on. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexam_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep observing, keep questioning, and go crush those exams.